The paper 5D Neural Surrogates for Nonlinear Gyrokinetic Simulations of Plasma Turbulence by Galletti et al., 2025, proposes a novel method for training neural surrogates for 5D gyrokinetic simulations to accelerate the deployment of commercial energy production via nuclear fusion. The authors extend a hierarchical vision transformer to 5 dimensions and train it on the 5D distribution function for the adiabatic electron approximation. They demonstrate that their model can accurately infer downstream physical quantities, such as heat flux time trace and electrostatic potentials for single-step predictions, 2 orders of magnitude faster than numerical codes. Introduction. Nuclear fusion and plasma turbulence. Nuclear fusion is a promising approach to generating clean and sustainable energy, but it faces challenges in achieving commercially viable power generation. One major obstacle is understanding and controlling plasma turbulence, which can significantly degrade plasma confinement. Plasma turbulence is a complex phenomenon that arises from the interaction of charged particles in a magnetic field. It causes the plasma to diffuse towards the reactor wall, resulting in a loss of heat and particles. Gyrokinetic simulations. To model turbulence, physicists use gyrokinetic simulations, which evolve a 5D distribution function over time. These simulations are computationally expensive, requiring up to weeks for a single run to converge. This makes it unfeasible for iterative optimization and control studies. Neural surrogates. To address this challenge, the authors propose using neural surrogates, which are deep learning models that can approximate the behavior of complex systems. Neural surrogates have been successfully used in various scientific domains, including weather forecasting, protein folding, and material design. In the context of plasma physics, neural surrogates can potentially reduce the computational cost of gyrokinetic simulations while maintaining accuracy. Related work. Machine learning for gyrokinetics. Most existing machine learning approaches for gyrokinetics focus on surrogate models of turbulence that adopt the quasi-linear approximation. These models have been used for interpretative and predictive modeling, as well as control studies. However, there is limited work on surrogates for higher fidelity models that capture the full complexity of plasma turbulence. Neural operators. Neural operators are a class of deep learning models that can learn mappings between function spaces. They have the advantage of being resolution invariant, meaning they can operate on inputs of varying resolutions. While the author's proposed model, 5D Swin UNet, is not a neural operator, they aim to extend it to one in future work. Methods. Data generation. The authors generate data using a state-of-the-art nonlinear gyrokinetic solver called GKW. They run GKW with adiabatic electrons for different values of ion temperature gradient, ITG, which is a key parameter that drives plasma turbulence. The simulations are initialized from noise and evolve through a linear phase and a saturated phase. The authors collect 5D fields of resolution, 32 by 8 by 16 by 200, 55 by 32 by 2, every 20 steps to ensure sufficient change. The dataset comprises 5 trajectories, resulting in 660 training samples and 1 unseen trajectory, 165 samples. 5D Swin UNet. To process the 5D input, the authors generalize the hierarchical Swin transformer to an arbitrary number of dimensions. The Swin transformer is a type of vision transformer that uses shifted windows to reduce the computational cost of self-attention. The authors extend this approach to 5D and call their model 5D Swin UNet. Evaluation. The authors evaluate their method using 3 approaches: visualizing the outputs of the surrogate model and comparing them to the ground truth data, visually inspecting the electrostatic potentials predicted by the surrogate model and comparing them to the ground truth. Evaluating the accuracy of the heat flux time trace predicted by the surrogate model. Experiments. The authors train 5D SWIN U-Net for next-step prediction of the nonlinear gyrokinetic simulation. They split the data according to trajectories into training and validation, evaluating on one holdout trajectory and using the remaining ones for training. They train their model for 100 epochs and evaluate every 20 epochs on the holdout trajectory. Distribution function. The authors visualize the predicted 5D field of the distribution function over time and find that the model prediction generally aligns well with the ground truth. Electrostatic potentials. The authors obtain the electrostatic potentials and provide a visual comparison of the predicted and ground truth electrostatic potential. They find that the vertical wave vector is well reproduced, but there is a misalignment with respect to the first mode, zonal mode, that represents the zonal flow. The authors attribute this to an imbalanced dataset, where the saturated phase with a stronger zonal mode is overrepresented. Heat flux time trace. The authors assess whether the model correctly infers the heat flux time trace of the holdout simulation, ITG equals 6.9. They find that the model predictions align very well with the ground truth heat flux time trace. This indicates that 5D SWIN U-Net successfully learns to capture parts of the underlying physics. Efficiency. The authors find that one-step prediction only requires 360 milliseconds on average for 5D SWIN U-Net on a NVIDIA A100 GPU, while the numerical solver GKW requires approximately 80 seconds using 64 CPU cores. Therefore, 5D SWIN U-Net is around 2 orders of magnitude faster than GKW. Conclusions and future work. The authors present a neural surrogate model for nonlinear gyrokinetic equations modeling turbulent transport in plasmas. They propose a neural surrogate that operates in 5D space, namely 5D SWIN U-Net, and demonstrate that it accurately captures the underlying physics for single-step prediction. Their work paves the way towards neural surrogates for 5D turbulence modeling for nuclear fusion. Future work. As future work, the authors plan to incorporate additional diagnostics to verify that the surrogate model accurately captures physics beyond electrostatic potentials. They also aim to include a separate head for explicit prediction of electrostatic potentials to alleviate the requirement for expensive GKW calls. Additionally, they aim to achieve stable long-term autoregressive rollouts with their surrogate model, which is currently hindered by the overemphasis on the zonal flow. Finally, they envision extending this work beyond next-step prediction to neural operators and enabling transfer from lower-fidelity simulations to higher-fidelity ones.